In this question, we've got an unidentified compound, and it contains chlorine, oxygen, and sulfur. And we've been provided the percentage abundances by mass, or at least, we call it percentage composition by mass of each of these elements. And we've been asked to figure out, okay, well, what's the empirical formula? Okay, well, the first thing I'm going to do is I'm going to have a go at effectively adding up the values that we've got here, right? And if you do have a go at adding them up, you should, I don't think in this instance it gets to 100. You should get 99. Just write this down. You should get 99. So this is effectively like 59.61 plus 13.43 plus 26.95. Right? You should get 99.99. Right? And we're going to assume, for the purpose of this question, before we go into the assumption, you can see that that number is effectively extremely close to 100, right? More or less, it's almost if I was to say I want to round this to 1 decimal place, for example, it's basically 100. But this in any case, what we're going to assume in this instance is that, okay, well, this is approximately 100, and we're going to also further assume that the total sample size we have is 100 grams. Okay. Now, as you might understand, that one assumption kind of hinges on the other one, because we're effectively rounding this to 100, right? Equals 100. Even though these numbers are not, they don't exactly add up to 100. They add up to like 99.9. But I'm not actually going to modify these, right? So I'm just going to go ahead with the question with these, and we would still come. We'll see how we get on. Now, when we make the assumption, what does that enable us to do? Chlorine, as you can see, is 59.61, right? Grams. So because of that assumption, we can say this is 59.61 grams, right? So that's the chlorine. Oxygen, we can say that's 13.43 grams. And sulfur, we can say that's 26.95 grams, right? And the assumption we're making is that, okay, well, that more or less amounts to 100 grams. In this case, I guess, plus or minus 0. 0.0, maybe 1 or 2. But anyway, we're going to use these numbers now. So, but we need to be able to compare the actual amount of the elements, which at the moment we're not easily able to do because each of these have different molar masses, right? But we can get them to a state we can compare them, given if we convert these to, for example, moles, we can now actually compare, okay, well, this is the amount of substance of this is the amount of substance of that. Okay, we can make some molar comparisons there and then get closer to working out our empirical formula. So that the equation we're using in such an instance is the moles equals, and that's N for moles, equals mass divided by the molar mass, right? MR in grams per mole. Yep. Now, the other thing we're going to do is, for some of these, you may know what the molar masses already are, like all the relative atomic masses for the elements. especially for oxygen, right? But I have a periodic table here, so we can just kind of use that to work out the molar masses. So we're gonna just list out what they are in each case. So Mr for Cl, Mr for oxygen, Mr for sulfur. So we can see for chlorine here, if I just move this slightly along, you can see a broader picture of what we've got. So you've got our chlorine, sulfur, oxygen. This is just kind of just effectively this. This question is quite convenient. We've basically got this L shape here, which is what we're working with effectively, right? So I've just expanded it over here. But what are we working with? We're working with 35.5, oxygen 16, sulfur 32.1. Right, so these relative atomic masses, this is effectively, they are the molar masses of the elements we're working with. Right, I'm just going to put a small kind of line here, right? Okay, so what we need to do at this stage is, yeah, I'm gonna, in the interest of economy of space, I am gonna move things slightly. So, but I'm gonna write out what the calculation is here anyway, and then I'm gonna write the answers out with a bit more space. So, as we can see, we need to do the mass divided by the molar mass, right? So, divide this by 35.5, divide this by 16. Divide this by 32.1, right? And I would invite you to have a go on your calculator to work these various values out, see what you get, okay? And okay, so as I said, what I'm gonna do is I'm gonna actually write out this, I'm gonna write it somewhere else. So I'm going to just write it here just so we have a bit more space. And I'm going to write these as molar. So we're just going to write N equals, right? And then I'm going to just write out the ratios next to it. So for the first one, when you did this calculation to 5 decimal places, we get 1.67915, right? And that's for chlorine, so I'm just going to put a Cl here. And then for oxygen, when we do this calculation, what you should get is 0.83938. So that's for oxygen. And for sulfur, if you do that calculation, what you should find you get is 0.83956, right? And at this stage, we are looking, as we know, we're looking for the simplest whole number ratio, right, between these different, these different elements. And as you can see, we don't have whole numbers at this stage. We have various numbers. What we're going to do to try and move things towards that objective is we're going to divide each of the values we have here by the smallest value among them. And in this case, the smallest value is oxygen. The moles of oxygen in this ratio. So we're going to divide all of them by that number associated. So 0.83938. Okay, and when we do the working out for this, what are we going to actually find? Well, we're going to find that we get 1 here, right? I mean, you can kind of just see that we're dividing something by itself. And for the others, for sulfur, we get 1.0021, and for chlorine, we get 2.00046. Okay, so when you take a look at these numbers, inspect them, like on a visual inspection basis, what do we notice? Well, when I look at these, what I notice is that if we were to round these numbers to 2 decimal places, every single one of them is going to be an integer value, right? And as we recall, we made an assumption at the start of, not that this assumption is the main reason we're going to do the rounding, but as we do recall, we made an assumption at the start of this process that these values all added up to 100, right? Even though really mathematically speaking, they add up to 99.99, right? So I mean, when we put that to 1 decimal place, it's basically 100, right? And with these numbers here, when we put all of this to 1 decimal place, well, we get integers. This, I mean, so here, what we're gonna find when we do that rounding is you're just gonna get 2, 1, 1. Okay. Now at this stage, when we look at these numbers, do we have the simplest whole number ratio between these elements? I say yes, we do. We have the simplest whole number ratio between these elements, and on that basis, we can say that associated with the Cl would be a 2, associated with the oxygen would be a 1, associated with the sulfur would be a 1 also. Right, and of course in the final formula, this is not how we're going to write it, right? We're going to write Cl2OS. Okay? So is this our empirical formula? Yes, this is our empirical formula. Cl2OS. Now, you may commonly come across this in a bit of a different format, and I'm not referring to I'm referring to the actual formula that you see. So you may come across, for example, SOCl2, and in terms of reactions, well, I would invite you to have a look at what SOCl2 is, what it's used for, what the charge usually is associated with it, just out of, if you're curious anyway, you might find that interesting. Okay,